So we want to continue with chapter 8 and kind of summarize, because we got interrupted last time. We were looking at a current mirror as a way to bias analog integrated circuits on chip. And using those, we could use a technique of current steering to derive any type of bias that we wanted or we needed. And then we were going to look, we were looking at the current mirror as a current amplifier. And with any amplifier, the main three metrics or quantities that we want to know are the input resistance, because we want to know how that amplifier loads whatever is driving it. The output resistance, because that has to do with how much the load loads the amplifier and the impact of the output resistance on the ability of the amplifier to drive the load. And finally, the gain. So we were looking at the current gain for the current mirror. So we had gone through as far as deriving. So this is chapter 8, current mirror as current amplifier. So we had gone as far as deriving this expression for the current gain of the current mirror. So the GM of the output transistor over the GM of the input transistor, and that was divided, multiplied by this expression. And the output resistance is the output resistance of both transistors, because they are the same, or rather for the second transistor. And also we were recalling that GM, the transconductance of the transistor, is the mobility of the majority charge carrier times the capacitance of the oxide or the gate, for the gate, the oxide for the gate, times the width to length ratio. So those are the electrical width and length ratio of the transistor times the overdrive voltage. So that was the, because what we want is some type of expression that relates the width and length of the transistors. We really, that's the only thing that we have control over in integrated circuits. So if we substitute the GM in the expression above, we get that the gain, the current gain, is going to be the width to length ratio of transistor 2, and you have to refer to the schematic of the current mirror, divided by the width to length ratio of transistor 1 times the quantity that we had before, times the output resistance of transistor 1. And put that there. So that's for transistor 1. Now, this, when you design the transistor, this quantity is going to come out to be very close to 1. And because of that, then we get the gain that is dominated by the width to length ratios of the transistors, and normally the lengths are the same, and you just have to size the widths accordingly to get the gain that you need. So that's a nice result. Okay. Now that we have current mirrors and we can generate biases for our circuits, the next step when we look at these building blocks of analog IC design, specifically amplifiers and op-amps, which is where we're going, now we want to generate a basic gain cell. So it's going to be kind of like the workhorse of the amplifier. So we're going to look at what is the basic gain cell, and after that we're going to develop some other blocks, and hopefully eventually we put it all together. So let's look at the basic gain cell.
Hey, Professor?
Yes.
Can you let Saad in from the waiting room?
Who?
He's not in already.
Who's in the waiting room?
Saad should be, unless
He's already.
Yes. Okay. Sorry about that. Thank you.
All right. So basic gain cell. And this is going to be essentially a common source amplifier. So it's going to be common source. And we're going to use a constant current source for biasing. So we just looked at the current mirror. And also, we're going to use a constant current source for loading. So remember that the common source amplifier, the gain is proportional to the load. Now, since we need high gain for this basic gain cell, the loading current source is going to have a large output resistance, which we need for high gain. So that's one of the characteristics of this basic gain cell. Overall, for an amplifier, that's not great, but we're going to do something about that as we go through it. So we're going to do something about that. Now let's look at figure 813 in your books, which has the topology of this basic gain cell. So hopefully you can see the screen there, and we are referring to the top because we're not doing BJT. So this is the very basic gain cell of a common source amplifier. And here we have the small signal model. That's what we're talking about. That's going to be our basic gain cell. Very simple. Okay. So keep in mind this small signal, because again, we're looking at this as an amplifier, so we're going to look at the same quantities. What is the input resistance? What is the output resistance? What is the gain? So if you keep looking at that small signal model, you can see, as we have seen, since we have the input into the gate, the input resistance is virtually infinite. And then the gain is very simply going to be voltage gain minus the transconductance times the output resistance, and then the output resistance is just going to be the output resistance of the transistor. So very simple, okay? Now with that in mind, let's recall a couple of things. Let's just recall this. The GM is the drain current divided by the overdrive voltage divided by 2. Now, a lot of, as we get more into this, very important but basic transistor circuits, one thing that is very important is chapter 5, where, and this is from Electronics 1, where you go through this, I keep recalling this basic relationships of the transistors. I mean, the assumption is that is carried from chapter 5, which is not part of this course, but it builds on it, okay? Now, this expression, okay, another way of expressing GM is, and this is an N channel, so the mobility of electrons times the capacitance of the oxide and width to length times the square root of the drain current. So that's part of the square law of the operation of the transistor. And the output resistance is VA, called the early voltage. We'll see what that is, or if not, review chapter 5. So VA is equal to VA prime times L. Therefore, the gain can be written as that voltage divided by half the overdrive voltage, or another way is same thing, okay? And if we put those together with the previous expression that had the square roots, we have that the gain is VA prime mobility of electrons, capacitance of the oxide, divided by the square root of the drain current. So that is the final expression that relates the characteristics of the transistor with the geometry of the transistor. And the drain current that we set with our current source or current mirror with biasing, and we have the gain of this basic gain cell. So these are characteristics of, well, this is characteristic of the material. This is a characteristic of the process that we're using to build the transistor, and so is this. Okay, so again, to get the gain that we need, we just have to set the W to and draw the transistor accordingly, and then set the biasing of the drain current with our current source or current mirror, and we have the gain. So attainable numbers for this gain realistically is going to be 10 to 40 gain. And when we actually build an op-amp, you can have multiple stages of this basic gain cell or better modified gain cells that we'll see later. But you can see how we can get to that maybe more than 10,000 type of open loop gain that op-amps have. All right, so let's go back to look at figure A15, okay? And let's start looking at how this gets implemented for real. So we have here this transistor Q2 is going to act as the current source load of this basic gain cell. And let's take a look at what the effect of that current in the overall circuit. Okay, that's the next thing that we're going to do. So now, when we put this transistor with a constant VG that we use current mirrors and biasing and current steering to generate, this is a constant voltage that sets that drain current through Q2, and that is our load to the common source basic gain cell or basic gain transistor Q1 of this amplifier. We have our amplifier, and it looks, from a small signal perspective, it looks like part C of this figure, okay? And that's what we're going to be talking about next, okay? So that biasing or load is going to look like a current I with an output resistance across it, which we're going to call RO2. So these quantities are going to be important as we make the next derivation, and we look at it in the from a small signal perspective. Now, also notice that this transistor here, Q2, is a P channel, and of course they're both all the transistors that we're talking about are depletion, or actually enhancement type transistors. So keep all that in mind as we go through the next set of derivations. But this is what we are referring to, this figure. So that's important. Okay, so writing the basic drain equation for the load transistor, we have that the current I, so that's what was in the diagram, is going to be 1/2 the mobility of holes. So we're talking about a P channel. The oxide, the oxide capacitance is the same for both. And then the width to length ratio of the P channel and the source is tied to VDD. We have the constant voltage at the gate, and then we have the threshold voltage for the P channel. And all that is going to be a square. Okay? The output resistance is going to be related to the early voltage for transistor 2 divided by the current. Therefore, the voltage gain, if you look at the small signal model, because of this output resistance, the voltage gain of the actual transistor, the N-channel common source that is doing the amplification, is going to be reduced. So if you look at the small signal model, you'll see that both output resistances for both transistors are in parallel. So my overall voltage gain is going to be the GM of transistor 1, the N channel that is doing the amplification. And notice that these are inverting. This is an inverting amplifier. That's what the, because of that minus sign that shows up in the equation, and also because the direction of the current source, GM times VGS of the N channel common source. And now that's going to be multiplied by the parallel combination of both output resistances. And you can see that from the small signal model. So when you put two resistors in parallel, you always get a smaller value. You always get a smaller resistance. So this is a gain reduction due to the load of the amplifier, the load on the amplifier, where we're using Q2 to load Q1. Okay, so we need to do something about that as we keep increasing these blocks that we need to eventually make an op-amp. And then the solution is in figure 8.17 in your books. So let me show that. So what are we going to do about that? Because we want to increase the voltage gain, okay? We're going to have to do an impedance transformation, okay? And what we want, if you imagine that we have this box here between the load and the drain of Q1, which is the amplifying transistor, okay? What we want to do for this block is to pass the current. The current here that is given by the GM of transistor Q1 times VGS, which is the input voltage into the gate, okay? So we want to pass that current right through, but also raise the resistance level so that parallel combinations of resistance or output resistance eventually doesn't get diminished. So what this functionality that we're describing is essentially a current buffer. So it is a type of amplifier that doesn't amplify voltage, but gives us current buffering or increases the current. Okay. And if you go back to the basic configuration for transistor, single transistor amplifiers, the one configuration that gives us that capability to do impedance transformation is the common gate amplifier or a common gate transistor. Okay, so that's what we're going to add to the basic gain cell to minimize or to lower the effect of the load on the gain of the overall amplifier. Okay. So now we're going to have in between the load, and here we're showing as a resistor, but that is our original load. We have this box here, and that box is the common gate that we have biased with some gate voltage. Again, these are biases that we can generate with the current mirrors and current steering that we talked about last time. And we have the input into the source and the output out the drain. Okay? And these are the equivalent, this is the equivalent circuit of the common gate amplifier, okay? Where we have the input into the source. So that is our current from the drain of our original common source amplifier. And here's the current at the output, the current gain at the output, the drain. And then this is our original load. And this model allows us to calculate that input resistance that is so important, because we're going to see that's going to allow us to transform the output resistance that the amplifying common source sees. So essentially, this common gate is isolating the low output resistance of the load so that the amplifying common source sees a higher output resistance. And when we go back and calculate the voltage gain, which is the minus GM of the common source amplifier times the parallel resistance of the parallel combinations of the output resistance of the common source itself and whatever is seeing at that node, at the drain of the common source, is higher, and we don't get that gain reduction. That's essentially what we're doing. So here you have the current at the source of the common gate. This is the common gate amplifier, and the gate is common gate, so the gate is grounded from a small signal perspective. And this allows us to calculate the input resistance. And this is the drain. This is the drain, or this is the drain of the common gate amplifier. And again, this is just a small signal model of the transistor. We have GM times VGS, which is going to be a constant. And here we have the output resistance of the common gate. And then that goes into the load. So because of this combination, and mainly because of the current source that is built into the model of the transistor, our amplifying common source sees a much higher output resistance at this point. Okay? So keep that in mind, because that figure is going to be very important for what I'm going to do next, which is exactly deriving that and seeing, so you can see how we get a higher output resistance and therefore a higher gain eventually. So let's just take a look at this figure specifically and derive some of the expressions that are here. So for what I'm going to be doing next, I'm going to be referring to the quantities in this figure. So if you refer to the figure that we just looked at, the input resistance is defined as the voltage at that node, the voltage seen by the drain of the common source amplifier divided by the current into the source of the common gate. Okay, so I can write that voltage as the current into the source of the common gate plus the current through the drain of the common gate amplifier. So that is the GM of the common gate transistor times the bias voltage. And then that's going to be multiplied times the output resistance of the common gate. And then another part of that voltage on that other end is the voltage across the load. So that is that same current, because remember that all the current that goes into the source of the common gate is seen at the drain. And then that current is going through the load. So the voltage at that other node at the drain of the common gate is that current times the load. Okay. Now since we have a common gate, since the gate is grounded, it's a common gate, then the voltage Vx at the source is minus VGS. And that is the gate to source voltage of the common gate, which means that VGS is minus Vx. Okay. If you apply that to this expression over here, okay, and do some manipulation of the some algebraic manipulation, you get the Rn again from this expression so this is the input resistance that we see at the at node X or into the input of the common gate. If GM for the common gate transistor times the output resistance of that transistor is greater, much greater than 1, then my input resistance is can be approximated by 1 over GM plus the load resistance divided by GM times RO. Okay? And then I have, just gonna write it kind of over here. And then I have a relationship because GM times RO is related to the gain. Okay? So let's keep looking at the current gain that is provided by the common gate amplifier or transistor. So that current gain is going to be the output current of the common gate divided by the current of the signal of the overall circuit with the common source. So before we go further on that, let's take a look at figure 820. Okay, so now here you still see the common gate over here, and we're going to be looking at the current gain of IO, which is the output current of the common source, but it's also the same current that is going out the drain of the common gate. Okay? So that's basically what we're talking about. So again, current gain is that IO divided by signal current and what happens is that there is a current division that happens because of the transconductances of the transistors. All the while from that common source through the common gate to the load. Okay? And then that is going to be GM plus 1 over RO, so your basic current division, so that is at the source of that is at the seeing at the source of the common gate amplifier. And we can manipulate this a little bit, okay? And that is going to look like so I can make this look like that, okay? Now, remember that this is a current buffer. It's going to be providing neither voltage nor current gain is going to be providing an impedance or a resistance transformation as seen by the common source. So it's going to make the output resistance of the load look larger to the common source original amplifier. Now, because of that, current gain must be about 1. So that's the whole current buffer. Okay. And if I look at this expression, to get that, what I need is, so we did this manipulation to get this so we could look at this expression and say, well, I have a current buffer. I want a current gain of 1. What needs to happen to make, so that happens? What, from a design perspective, and remembering that the only thing that I can manipulate is the width, the electrical width of the channel, or the geometric length of the transistor, how do I make that happen? Well, if I look at this expression and I want this approach 1, because I have a current buffer, that also means that I want a large GM. And which implies that, remember that GM is the mobility times the capacitance of the oxide times the width to length ratio. So if I want a large GM, I want a large width to length ratio. And since normally the length is fixed by the technology, that implies that I want really a big transistor. Okay, that's all. So we have proven to ourselves that if I have a big common gate current buffer, I can actually do the necessary impedance transformation for my common source to see a large output resistance of the load and make my gain higher. So it's not going to reduce the gain of that common source amplifier. Okay. So let's take also a look at figure 821. And now let's look at it from the other end, because we also, everything that we looked at the input resistance, we just look at the gain, the current gain. Now let's look at the output resistance of that common source amplifier. So looking at it from the other end, and now Vx is going to be, or our test voltage to calculate the output resistance is going to be the voltage at the drain, which is the output of that common gate amplifier. So this is the reference, small signal model that we're going to be utilizing in the next analysis. Okay, so let's go back to that. So referring to that figure 821, the output resistance as seen at that node is our test voltage divided by the current. And again, if we look at the nodal analysis at that node, I can write that Vx is equal to the current minus the current source, and that's going to be GM times the biasing voltage at the or the gate to source voltage of the common gate, not biasing because it's not, there is no biasing. It is biased, but with 0 volts, times the output resistance plus the current times the resistance at the other end, at the source of the common gate. So this is the same type of equation that we did to calculate the input resistance, but we're just looking at it from the other end. But it's the same type of rationale or analysis, okay? Then we can also write that the negative of the gate to source voltage for the common gate is Ix times Rs, and if we apply this into that and this into that as well, we get that the output resistance or by RO plus 1 plus GM RO times RS. Now, normally, remember, I have control over GM and RO to a certain extent. If I can make this observation that if GM times RO is much greater than 1, then the output resistance is basically RO plus GM RO times RS. Okay? And furthermore, let me, so I don't erase everything, let me just erase this to make space there. And I'm going to kind of finish this in this area. So if I make another assumption, which is reasonable as well, and that is that, again, because I can control GM, if GM times RS is much greater than 1, then my output resistance is essentially but this here is my gain. So you can see how the gain has transformed the impedance or the output resistance seen by the load, and also seen by the common source amplifier. So let's summarize what this does for us. Make sure I'm not skipping any pictures. Let's summarize what the common gate amplifier does for us when we put it between the common source, which is the actual transistor doing the amplification, and the load that we need after that common gate. So this is the summary. Of the common gate circuit. Current gain. About 1 because it is a current buffer. The output seen at the source as we related to the output resistance of the common gate is increased. Is increased by the GM times RO. And then from the load perspective, the input resistance seen at the other end, as seen by the load, is reduced by the same factor. So again, the output resistance that the common source sees that is providing the amplification, so its gain doesn't get reduced, is seen as much higher now and amplified by a naught. What the load sees is reduced. But that biasing current load that we see, that we have in there because it's necessary for the common source, is reduced by, as it relates to the input resistance at the other end, at the input of the common gate, and that is reduced by the gain. And here's a nice figure, okay? So this is the common gate over here, and seeing the resistance seen over here by the common source, and here what is seen by the load, and these are those relationships, okay? So now, as we build this basic gain cell, we have our common source. We put a common gate circuit that does current buffering, and then we have our load. So far, we have now the 3 transistors in there. Now let's look at another configuration that is going to be an upgrade from this. And we're going to, that's called a Cascode amplifier, and it's shown in figure 828. Okay? So when you put all together, okay, the Cascode looks like this. We have our constant current source load, okay? In here we have our input, but then we have this transistor here, which is biased, which is also a common a common gate from a small signal perspective, okay? And we take our output here at the drain of Q2. So let's take a look, based on this figure, to the same quantities of interest that we always look at for amplifiers. And here we have a couple of small signal representations of the Cascode. Okay, so we're going to be referring to these quantities as we go through the following derivation. Okay. So referring to that circuit, I want to know, the things that I want to know is the voltage gain, and that's going to be defined by the output voltage divided by the input voltage. I also want to, so that the Cascode is a sort of a detour that we're taking, okay? So it's as if we were talking again about just the common source. So don't confuse what we just looked at, which is the one transistor common source, with the common gate with this Cascode implementation. This is just a totally different circuit. It's just a voltage amplifier that is using a biased, it's almost the same, but not really, because it's not truly a common gate, although it is from a small signal perspective, but it's not the same, because later on we're going to essentially apply the Cascode idea to what we just finished talking about, which was a single common source and followed by a common gate. So we're going to sort of apply that idea later on, okay? So let's just look at this in its own merits, as is shown in that figure 828, and try to find what the voltage gain is, as well as the output resistance. So output resistance, if you look at just the figure, pretty trivial to look to see that the output resistance is the transconductance of transistor 2 times the output resistance of transistor 2 times the output resistance of transistor 1. Okay? And then the output voltage is going to be minus GM1 for transistor 1 times the input voltage, so that's the VGS of transistor 1, times the output resistance that transistor 1 sees. Therefore, the gain is the transconductance of transistor 1 times the output resistance that it sees. And if I substitute RO, if I substitute for RO this expression, then I get that the gain well, now this is interesting, because now I start getting some interesting voltage gains, and they can be pretty high, which is what I want. Now with this Cascode, if I, which is not unreasonable, if I say I'm just going to make the transistors the same, okay, and let's just call that GM. And if I make him the same, arrow 1 is equal to arrow 2 equal to arrow, okay? And if I define, so I'm going to come over here. If I define the old gain by GM times RO, then this voltage gain that I've been talking about is minus GM RO square, which is which tells me that this voltage gain is the square of my old gain for the single transistor. So with this Cascode circuit, now I have squared the gain, and that's really really interesting and beneficial. So Cascode, so the circuit that we're talking about, gives me the squaring of the gain. Okay? So now that I have the Cascode concept, I previously looked at the output resistance transformation effect of a common gate. Let's add a PMOS load and see what happens. Okay, so let's add a PMOS load and see what happens. So in the Cascode, we're not just rehashing the common gate, but there is some common gate effects there. Okay, that's what I've been sort of trying to keep it different, but also getting you to recognize the similarities as well. So let's look at what happens if we add a PMOS load to the Cascode. Okay, and then that's going to be shown in figure 829. Okay, so here you can see the Cascode, and here we're adding a PMOS load. Okay, so again, this figure and the corresponding small signal model is here in part B of the figure. That is what we're going to be talking about next. So keep that in mind, okay? So for the Cascode with the PMOS load, if you refer to the figure, you can see that the load resistance is the output resistance of that PMOS load, which is transistor 3. And that is the load resistance that the Cascode part is going to see. Okay? That is the load resistance that the Cascode is going to see, but the voltage gain is going to be the GM of the first transistor times the output resistance seen by it in parallel with the load resistance, which is R03. You can see that from the small signal diagram. And based on what we did before with the Cascode, I can write that the voltage gain is minus GM1 times GM2, the second transistor, the Cascode or transistor on top of the Q1, times R02 times R01. So you can see here the part of that gain square, okay? But now with the load, this expression is in parallel with R03 because I have to take that into account. Okay? Now, I can make my load resistance to be much smaller than because that's normally what happens, and that's the case, that the RL is much smaller than the RO. So the RO seen by the Cascode is much larger than the load resistance. If that is the case, and I take that into account in this expression, then, because I need that load, I mean, the load is necessary to develop and to have gain. So if I apply that to the voltage, I see that now this expression becomes about minus GM1 times R03, which is the output resistance of the PMOS load. And that's annoying because if you recall this expression, that looks like just the one transistor gain. So that PMOS load that I need has nullified the Cascode effect, which was so nice of squaring the gain. So Cascode effect nullified. So not happy about that. Now, I don't think we're going to get to the last chapter that is in the syllabus, but if we did and we had the time, and I hope that get there someday, not this semester, but some semester, is chapter 10, which looks at these amplifiers after we have gone through building them. And now that we have gain and all that, something that we have to take a look at is the frequency response. That's very important. We're not looking at the frequency response here. All this is from a frequency perspective, we're assuming that everything is going to work out. We're not taking into account any frequency response effects. And we're looking at the small signal and biasing, but we're assuming that the amplifier can handle and has an infinite bandwidth for a we care, but that's not the case. There are other effects and other capacitive components that we can put into the small signal models to do all the analysis that we're doing. We can do it as a Laplace type analysis and see that it's frequency dependent, all these quantities. So we're not going to be seeing that, but I mentioned that because this PMOS load, even though it nullified the Cascode effect. Just take it from me that it increases the bandwidth. So, but it increases the bandwidth. So that's sort of a consolation prize there. Okay. But we don't have to settle for this. Okay. Because the same way that we use the Cascode effect to increase that gain, we actually can apply cascoding to the PMOS load so that it doesn't nullify the Cascode gain. So that we can explore that at least, but that's going to be the case. So if you look at figure 831, here I have my original Cascode. Those are Q1 and Q2. And then I have a PMOS load, or a load made out of two PMOS with cascoding. Okay? And those are Q3 and Q4. Okay? So now I have 4 transistors so far, okay, in my basic gain cell. And again, this bias, the actual signal input is coming into the gate of Q1. That's the actual doing the amplification. The other ones are just constantly biased. And I generate VG4, VG3, and VG2, again, with current mirrors and current steering, which we discussed at the beginning of the chapter. So let's look at the effect of this 4 transistor circuit, where we have a Cascode amplification and a Cascode PMOS load. Figure 831. Okay, and again we try to look for our usual quantities of interest, starting with the output resistance, and it's going to be GM3 times ARO3 times 4. That's the output resistance of the 4th transistor. And again, we can define a voltage gain. Okay. And VO over VN. And that's going to be the GM seen by the very first transistor, my actual amplifier. Everything else is loading, okay? Times the add out from what I'm going to call the N network, because that is made of the bottom 2 transistors, and they're both N channel, in parallel with the add out of the P network, which are the top 2 transistors, the P channels. And that is so this is for the N channels. So this is transistor 2 times the output resistance of transistor 1. Right here we have the cascoding effect of the two N channels, okay? And that, so this is times the, and this is very symmetrical and very elegant, actually. And here you have the P-channel output resistance that involves the cascoding effect of the two top end channels, Q3 and Q4. Okay. There is no reason. There is no reason not to make, from a simplicity perspective, not to make all the transistors the same. So if all the transistors are the same, the actual this messy expression, okay, reduces to one half the GM. So now the GM is the same because all transistors are the same, and the RO is the same. 1/2 is still an inverting amplifier, so it's minus 1/2 GM times RO square, which is minus 1/2 the original gain of the single transistor square. So we got rid of the nullification of the cascode effect with the cascode effect on the P network, and we recovered some of that high gain. We cannot recover it all, but we got half of it. So if the gain for a single transistor, let's say it was 40, now that A square is going to be 1600, so half of that is 800. So the cascoding with the 4 transistor maybe go from 40 to 800 on the gain from relative to a single transistor. So that is a factor of 20. So that's nice. Okay. So now I have a gain of 800 for a single gain cell. And if I use 2 stages, now that's 800 square. So that's a huge gain. But 40, you can see the point is that 40 is kind of on the high end. If we take the other end, let's say that is 10, okay? So I get a gain of 50, and if I use 2 stages, but that's at the lowest end, I get 2500. So between 2500 and 1600 square, somewhere I can get my op-amp gain somewhere in there, and that's usually what you see is between 10,000 and 20,000. So that's where it's coming from. Okay. All right. So let's see. Maybe I can finish the chapter today. So let's just keep going because yeah, let's do that. Now let's pivot and look at another circuit that is very important that we have talked about, which is the source follower, because at some point we need this current amplification to drive load and isolate that voltage amplifier whose gain relies on the load, isolate it and drive whatever load is there. We don't want the gain tied to the load. So the source follower allows us to do that. So let's take a look at that next. And that is going to be in just as a reminder for you, because that's just going to be in figure 885. So here you see an IC. Remember that the source follower, we had the load at the source and the input, of course, at the gate, but the drain was a signal ground. So here we have just Q2 and Q3 are a current mirror, which is just developing the load or the biasing, rather, not the load, but the biasing for the current, for the source follower. The actual source follower is Q1, and the input is at the gate, and that's Vin. Okay. Now, one thing that is in here that I want to call your attention to is the fact that when we have transistors stacked, like we have Q1 on top of Q3, and we've seen that before, but we're bringing it up here because it's simpler to manage and explain here than, let's say, in the context of the 4 transistor Cascode that we just saw. When we think about transistors, we think that the source and what we call the body are tied together. Most of the time, that's the case. We can tie it together, but it may be that sometimes that's not possible. And what that means is that the body of this transistor, because the CMOS transistors are really 4 terminal devices, and I've drawn that for you before. So there is a body that when we don't draw this terminal, the body, is because we're implying that the body is tied to the source. And if you buy a transistor with 3 legs, with 3 terminals, that's how it is. It is tied internally, okay? But that may not be possible when we are doing integrated circuits. So we have to take that body effect into consideration, okay? We have to take that body effect into consideration. And that is done here in this small signal model of the source follower. So given this figure and this small signal model, let's look at our usual quantities and look at our voltage gain. And we can see from the small signal model that that's going to be RL what this RL is the output resistance of transistor 1 in parallel with the output resistance of transistor 3 in parallel with the current source associated with the body effect. The body looks like another gate, and it much weaker, but there is a GM associated with it from that voltage from the body to the source. And you can see that if there is a current or an effect that is dependent on the voltage from the body to the source, if I tie the body to the source, that voltage is 0 and I don't have it. And that's what we've been doing, ignoring it. But when I don't tie the body to the source, then there is a VBS that acts like another VGS, and there is a current source associated with it, and therefore there is a GM associated with it, which we call GMV. GM is associated with VGS, GM is associated with VBS. Okay? These are real effects, but they are also small. And it's not unreasonable to say that the transconductance due to the body effect, it can be much smaller than the output resistances of transistors 1 and 3 in that small signal diagram, okay? But it's still real. If that's the case, then what this implies is that RL is 1 over GMB, or about 1 over GMB. So it is a real effect, and we have to take that into account. If we take that into account, we can see that our voltage gain is equal to there is usually a factor that relates GMB to GM. And we use it just to show that GMB is much smaller than GM. So that the effect is weaker. But we say that GMB is equal to chi GM, and that is normally so essentially GMB is about 10 to 20% of GM. That's how much smaller it is. So if I use this here and apply that to that expression, and you can see how my voltage deteriorates through the source follower, which should be 1. If I don't have the body effect, so with no body effect. So if I tie the body to the source, then I don't have this, and my voltage gain is pretty much 1. But that's not going to be the case when I cannot do that, okay? And then my output resistance is going to be the parallel combination of GM and the effect of GMB and which is close to is close to GM, 1 over GM plus GMV. Or another way of looking at that is 1 plus that factor that we define times GM. So you can see how the GMV has an effect on the output resistance. So I guess just to wrap up the chapter, I'm going to let, as you read through the chapter, look into some other things that are towards the end of the chapter. So there are some better current mirrors explained towards the end of the chapter, but this everything that we looked at here gives you a good basis and a good foundation as we build the circuits that we need to build an op-amp. But there are better current mirrors with better accuracy, with higher output resistance, which is a desirable thing. Lower voltage operation, so operating for what we discussed at the beginning of the chapter, that because of the small transistors and thinner gate oxides, the voltage range keep getting smaller, so you start operating very close to the threshold. So lower voltage operation is another desirable characteristic. So some of that is explained in towards the end of the chapter. For example, a couple of notable things are what is called the Cascode current mirror. So basically, this is applying the same cascoding principle to the current mirror that we started with, and you can see that if it was good for the amplifier, why not for the current mirror, right? So that gives you a higher output resistance, as seen at the node VO, which is where you're providing the bias, if you're using this to provide a bias or a load. So the RO now is, in this case, a specific circuit. The output resistance is the GM of transistor 3, but now is, and then that also is going to be multiplied by the output resistance of transistor 3, but also it gets multiplied by the output resistance of transistor 2. So you get a higher output resistance for this current mirror, which is a desirable thing. Another topology that has the same effect, so essentially that the output resistance gets increased, is what is called the Wilson current mirror, that looks like this. So it uses one fewer transistor in this topology. So you have here a couple of versions, but you can go through analysis the same way that we have seen or that we have done, and you'll find that the output resistance again is increased. In this case, the output resistance is GM of transistor 3 times DRO of transistor 3 times DRO of transistor 2. So those are just some additional additional comments as we end the chapter. So that's the end of the chapter.